Hey guys, welcome to my channel LeetCode Learning, and today we're gonna talk about another problem called LFU Cache. So the problem is marked as hard and its number is 460. So the problem says that you have to implement a data structure called least frequently used, which has a capacity, and you have to allow a put operation and a get operation. And whenever the elements in the cache reaches the capacity, the number of elements in the cache reaches the capacity, you have to remove the least frequently used element. So how will you do this problem? In general, like when I approached this problem, I used a brute force approach, which is a very simple approach, and I will go through that approach briefly. But then I tried to optimize it to improve the time complexity. So let's talk about the very brute force approach to solve this problem. So in general, what you can do to solve this problem is you can create a hash map of a key value pair. So Java has a hash map class. So in Java hash map, what you can do is you can create a key value pair where key is the given element and the value will be a node. This node is basically a user defined class which has four elements. So this node will have a key, a value, a frequency, and a time, or a counter, whatever you want to call it. So this is the node. So what you do is whenever you add an element to the cache, so whenever you do the put operation, you put the key and this node object into the hash map. So hash map will have some, for example, if you're given value, if you're given key is equals to 1 and value is equals to 2. So this is key and this is value. If you put this entry into the hash map, or the hash map which we define as a structure in this code, that will have something like key as 1 and a node class object which has 1, 2. By default frequency will be 1, or the starting frequency will be 1, and the time, let's say it's 1. And whenever we, let's say we access this object, we change the frequency and the time. So for example, this is the put operation. Now if I try to get the value of this key 1, then I return answer 2, but the map also changes. So map becomes 1 comma key is 1, value is 1, frequency is 2, and the timer is also 2. And for example, let's say if I put another object called let's say key 2 value 4, so the map will look like something key 2 value 4. So this will have 2 4 frequency 1, and let's say timer 3. So timer is basically a global variable which starts from 0 when the code initializes, and it keeps on incrementing 0 1 2 3. So what happens is, in this brute force approach, when you add a value to this hash map, you add a key node pair, and you just get the value from the hash map uh, using the key which is given in the get function, and you return the value. But the problem is that when you put a value and if the capacity is reached, then you have to iterate through through all the values in the map, and then you have to remove the value which has the least frequency. And if the frequency is same, then you have to remove the value which has the least time, because in the question it is given that if it is given that if the frequency of the two elements is same, then you have to remove the least recently used element. So the problem in this approach is that put up operation can have a time complexity of order of capacity. So the capacity of the map, a hash map which we created, will be this cap value, and the put operation can go up to order of cap, because if the size is reached, or the size of the elements, or the size of this map reaches the capacity, then you have to remove the element from this map based on the criteria given in the question, which is like same frequency, uh, least recently used, or the least frequent element. So this operation can take order of capacity size. Now how can you optimize this solution further? So I will discuss an approach which basically optimizes this solution to order of log capacity. So this will become, so for example, if capacity is n, then in the brute force it's order of n put operation. In the optimized one will be order of log n. So we'll optimize the solution to logarithmic time. Now how can we do that? So in the new approach, what we'll be doing is we'll create two hash maps. One hash map will have a key node pair, just like we have right now for quick access, and the second hash map will have a key doubly linked list pair. So that doubly linked list pair will be the one which will tell us what is the frequency of the element, or the least frequent element, or the least recently used element. To explain it further, let's look at this.
So what are the two hash maps we have? So the first hash map we have is of the same structure which we use in the brute force. So the first hash map will be of key and node pair. This is a similar structure which we used in the previous approach, in the brute force approach. And the second hash map we have is of frequency and a doubly linked list. And this second hash map will be the one which will optimize this brute force approach to logarithmic time. So how we do that? So the node we have here is contains a key, the given key in the question, or the elements key, a value, and the frequency, and a previous and next pointer, because this is the node which will be used in the second hash map in as a doubly linked list node. So how do you use this approach? So the basic algorithm says that when you enter an element, let's say we are doing put operation and we are entering key with 1 and value with 2, we create a node with 1 key, value 2, and frequency 1, which is the default frequency of a new node, and we add this new node to the primary hash map or the first hash map as key 1 and a node 1, 2, 1, and then we add this new node with frequency 1 into the second hash map of frequency and doubly linked list. So the second hash map will look like this: frequency 1 and a node 1, 2, 1. Now remember, this is the key, but this is the frequency. So let's say we add another element. Or let's say we add key 2 and value 4. So the new node will look like 2, 4, and frequency 1. So the new hash map, or the second hash map we created, this will again go in the same first frequency entry, and the new node will be attached over here. So this will be 2, 4, and frequency 1. Now how this doubly linked list will be used? So if we are trying to remove an element from this cache when the capacity is reached, we look at this frequency hash map and we pick the least frequency or the least frequent doubly linked list, which is 1 in this case, and remove the first element. So this first element will be removed. So for example, if the capacity is 2, and let's say we add another node with, let's say, key 3, value 7, and frequency 1. This is the new node which we are trying to add. We are trying to add this node into the cache, and we say that capacity is 2. Then we have to remove 1, 2, 1 from the node. And then we attach this 371 to the 1 frequency list after the previous node of 241. So we add like this. So this adds after this. So this becomes the first node and this becomes the second node. Now let's say after this put operation, we try to do a get operation, and we get the value 2 comma 4, or we get the node 2 comma 4 with key 2. What we have to do is we have to change the frequency of this 2 comma 4 node, and the frequency of this 2 comma 4 node changes to 2. So when we change the frequency to 2, we remove this node from here, and this 371 node becomes the first node in the first frequency list. So this becomes the first node in this with frequency 1, and we create a new entry in the frequency map with frequency 2, and we add the previous node whose frequency is changed after the get operation at the end of this new frequency list, or this new frequency list of value 2. But this is the first node, so this will be the first node in this list. Now let's say so the frequency of this is 2, not 1. So now let's say we again do the get operation on this node, then its frequency changes from 2 to 3, and we remove this node from this 2 frequency list, and we create a new frequency list of 3 and add it over here. And as soon as we remove this node from here, we also remove this entry 2. So this is the new hash map. Now, why this approach has a logarithmic time complexity? The reason is that when we are trying to remove an element after the capacity is reached, we have to remove the least frequent element. And in order to get a least frequent element, we have to either sort this structure, or we use a structure called tree map instead of hash map. So we use a tree map structure instead of hash map. So tree map has log n time complexity of insertion deletion. So in that way, we can simply pick the first element from this frequency list or the frequency map, and we can remove the element from that frequency list when we are trying to remove an element. So that is why this approach has log n time complexity. So this tree map structure helps to maintain a sorted frequency list in ascending order, and whenever we are trying to remove an element after the capacity is reached, we just pick the first frequency or the first entry of this tree map, and we iterate over the elements in that doubly linked list. If there is only one element, we just remove that element and remove that entire entry, just like we did with the 2. Otherwise, we just remove the first element. So this is how this approach works, and the complexity here is log of capacity. Now I will explain this approach more when I show you the code. So I have already submitted a version of this code, the optimized version, and I will just pick that up from my recent submission. And I will explain that solution to you. So as discussed, we have a class node structure. This has a key, value, and frequency pair, and then had next and previous pointers just to maintain a doubly linked list, and the frequency is by default 1. We have a primary hash map, which is just used to pick the values instantaneously, and then we have a tree map of frequency. So this tree map is basically a map of frequency and a map of frequency with doubly linked list, and this doubly linked list has a start and end pointer. That is why this map has a node array. This node array is basically just 2 values, start and end pointer of a doubly linked list. So for example, if this tree map has 3 frequencies, first frequency has elements xyz, then the order of insertion is xyz, and the frequency 2 has elements pqr, and frequency 3 is element ab. So this is how this tree map structure looks. Now how does the get operation work? So the get operation gets the value with the key given. If the primary hash map does not have that value, then we don't have to do anything, and we just return -1. If the primary hash map has a value, then we get that node from the primary hash map, and the frequency of that node has to be changed. So we use a function called change frequency. So let's look at that change frequency function. So this change frequency function has 2 parts. One is detached node and one is attached node. So this detached node, what it does is it detach the node from the current frequency list of this node. So for example, if this node has frequency 1, we detach it from that frequency list and then we increase the frequency of this node and we attach it to the new frequency of 2. So for example, if we are trying to, let's say, delete x from this tree map, and the frequency is 1, we detach it from the first frequency list and we remove x from here, and then we try to attach it to frequency list 2 and we attach it over here. So the attach function does this, and the detach function removes x from the first frequency. So now let's consider the case where we are trying to remove y, which is the middle element of the first frequency list. And this definitely is possible. For example, when we try to get a value y and the frequency of y changes to 2, we remove this y, we attach x and y together, and we attach that y to the new frequency list. So that's how it happens. So how does it work? So we go into this change frequency function, we remove y using the detached node. So if the node is middle element, this is how it happens. If the node is middle element, then we check whether the previous pointer is not null and the next pointer is not null. We remove y from the current frequency list of 1. We attach x to z, or the x next pointer to z, and the z previous pointer to x. We set both the previous and next pointer of current node to null, and we return from here. So this is how y will be removed from xyz list. Now if there is a case where the node which we are trying to remove is the end node or the start node. So if that is the case, then we first get the node pointers of that current frequency. So if the frequency is 1, we get the node pointers or the start and end pointer of that frequency, and we check if the current node y, so this is the current node is y, and the frequency is 1 for y right now. So we get the start and end node of the first frequency list, and then we pick y to delete it. So we check if let's say if we are trying to delete z, which is the end node in this list, and we get the start and end pointers, and when we try to delete z, we say that the previous is not null but the next is null, so z is the end node. So what we do is we just hold the previous value of z, which is y, and we set previous next to null, and the current node z previous to null, and we update the end pointer. So this updates the end pointer to y, because we have deleted z, so we have to update the end pointer to y. So the end becomes y here. And similarly, if you try to delete x, then we have to update the start pointer. So this next case is when we are trying to delete the start node. So we do the similar operation. We just shift the start pointer to point to the next value, which is y. So this is a very simple doubly linked list operation when we are trying to detach a node. And if there is only one element, that means this is the case when both previous and next of current node is null, then we remove that entire entry from the frequency map. So consider the case where there was only one element of frequency 1, let's say there was only x, and we are trying to delete x, then there is no need for this entire entry, so we delete this entire entry from the map. Now one thing I want to point out is that how are we trying to remove the least recently used element. So for example, if there are more than one elements of same frequency, so let's say the frequency is 1 and there are more than one elements, we remove the first element, and that will always be the least recently used element, because we always add the elements at the end of this doubly linked list. So they are definitely the most recently used. So for example, if y is currently used, it becomes the most recently used, and it attaches to the end of the new frequency list. So all the first element of this frequency list will be the least recently used in that particular frequency. So for example, if we are trying to delete an element from frequency, and so for example, if there is no entry for 1 and the least frequency is 2, then the p becomes the least recently used element in the frequency list of 2. So that's how we delete an element of same frequency which is least recently used. Now coming back to the same function of change frequency. So change frequency deletes the node from the current frequency list, then updates that frequency and attach that node to the new frequency list. So now look at the attach node function. So attach node function, what it does is it first checks whether there is an entry for that new frequency we have created. So if there is an entry for that frequency, so let's say the new frequency is 2 and there is already an entry here. So when we remove y, we just want to attach to the frequency list of 2 and which already exists. So here we first check whether there is an entry for that frequency. If there is an entry, we just get the frequency of this node and we attach at the end of this. So pointer 1, so basically pointers 1 is the end of the frequency list or the W list. So this is the end of W list. So we add this node at the end. We change the previous pointer of this node, and we also change the end of the W linked list. So now when we have added a new node, the end becomes the new node. But if there was no entry of that frequency, then we have to create a new frequency of 2 and we add the new node. So when there is no entry in the frequency list of that particular frequency, then we create a new node. So consider the case where, let's say we are trying to add a frequency 4, then there is no entry. So we add a new node, let's say C. Now C is the only node in this list. So C is the start and end. So in this particular case, we initialize both start and end as the current node, and this is how we attach a new node. So in the get operation, we just try to get a value from the primary hash map. If it does not exist, we get the node. If it does not exist, we return -1. If it exists, we get the node. We update the frequency and update the position of that node in the frequency map, and we return the value. Now with the put operation, when we are trying to put a value, we first check the capacity is 0 or not. If the capacity is 0, we don't do anything. Otherwise, we check whether the value or the key is present in the primary hash map. If there is a key present in the primary hash map, that means the capacity is not reached because the capacity is not increasing. So we don't have to bother about the capacity. We simply get that node associated with that key, we update its value, and again we change the frequency. So remember that whenever we do a put or get operation, we have to change the frequency. Now, if there is no entry of that key in the hash map, then there are two cases. Either the capacity or the size of the hash map has already reached the capacity, or it hasn't. So consider the first case where the size of the hash map is already equal to capacity, then we have to remove the least frequently used element. So that's why I have created a function called Invalidate Lfu. So what does this do is, it checks if the frequency map is empty, we don't do anything. Otherwise, it picks the least frequent element from the frequency map or the least frequency list, and then we get the start and end pointers of that, and then we just check if there is only one entry in that frequency list or there is only one node. Like in the case of 4, there is only one node C. We just remove that entire entry. We just remove the frequency.remove. We remove the entire frequency entry of that or the frequency list of that, or we just remove the first node. So pointer 0 basically points to the start node. So when there are more than one entry in that frequency list, we remove the first entry to remove the least recently used element, and we just shift the pointers. So next becomes next. So the next element previous become null, and the current element next become also null, and we shift the start to the next element. So start becomes the next element. So what it means is, for example, if we are trying to remove x from here, we remove x, so we map y previous to null, and then we change y to be the first start node, or the start node becomes y, and we also change x to null. So just to explain it further, so if this was the frequency list and we are trying to remove x, we we first remove x from here by changing y previous to null, then we change x next to null, and then we make the start node as y. So this is what happens here in the second case of this this function invalidate LFU when there are more than one entries of same frequency. So now coming back to the put operation, if the size is reached, or the size of the map has reached the capacity, we invalidate LFU and remove the least frequently used element or the least recently used element based on the frequency, and then we attach a new node. If the size has not reached, we don't do anything. We simply attach the new node using the attach node function I discussed earlier, and we also put the value into the primary hash map. So in this way, we can solve this problem in order of log capacity, because remember we are using tree map, and in order to enter new nodes in tree map, we have to do a logarithmic time operation of capacity or the size of this tree map. Now there is another solution for this, which is further optimized to order of 1 time complexity, and I will create a new video for that order of 1 time complexity, and I will post that in future. But this solution is pretty decent, and this also runs in a very efficient way. Let's try to run this quickly, and if you submit this, you can see that it already beats almost 88% Java submissions. So this is one of the way of solving this in log time complexity, and I will try to optimize it further with order of 1 time complexity and post it in a new video. So that's all for today, and if you like this video, please give it a big thumbs up.